Good morning, everybody, and welcome to the Biomedical Informatics and Data Science Grand Rounds. We're delighted to have you this morning. We're more delighted. In fact, I'm Chris Shute. I'm head of the section of BIDS, and we're more delighted to have my old friend and colleague, Emily Pfaff, speak to us today. I first met Emily when she was a graduate student. We worked on the NCATS translator program together, and I've been very impressed with her progress and maturity and contributions, not only in the NCATS translator, but more recently as a team lead on the N3C, the National COVID Cohort Collaborative. And of course, she's now a multiple PI on the NHLBI PASC grant. Emily received her BA from Wesleyan in Russian and European Studies. She got her MS from Chapel Hill, and it seems just recently, but it was actually going back a bit, her PhD at the University of Chapel Hill as well in clinical informatics. She is presently a research assistant professor at UNC, the domain scientist in the Renaissance Computing Institute, as well as co-director of informatics and data science for the CTSA at UNC. Dr. Pfaff, please welcome.
Thank you so much for having me. I am delighted to be here. And today I'm actually going to be focusing a lot on some of the work that we've done in tandem with Chris and others as part of the National COVID Cohort Collaborative, or N3C. But I am planning on making that a larger statement on how important EHR data quality is to the work that we do as clinical informaticians. And so with that, I will take it away. So today I am going to be talking about EHR data quality. And I like to call EHR data quality as something that we need to achieve somewhere between pragmatism and perfection. And we'll talk about exactly where between pragmatism and perfection we need to get as part of this talk. And I will be using N3C as a big example of EHR data quality. But again, I think the lessons that we've learned as part of N3C can really be applied to any number of EHR data-driven research projects. So early in my career, when I was a data analyst at UNC CTSA, an investigator told me in no uncertain terms in an email where he copied my PI that this data is junk. And I had provisioned an EHR data set to this individual, and there was the standard noise, but I certainly didn't feel like the data was junk, even if it had some caveats. And I was particularly offended because I am a real stickler for data as a plural noun, and I felt like he was really going against my sensibilities there. But the more important lesson was that data from the EHR can very easily be seen as junk from people who aren't used to working with it. And I took a lesson away from this, that it's not suitable for us as informaticians to sort of scoff and say, well, the data is not junk, you should just know better. Really, it's our job to let people know what the caveats are for working with EHR data and how they can separate the signal from the noise, because we know there is a lot of noise. And that's when I became very, very interested in not just EHR data quality from a technical standpoint, but really evangelizing this idea of there is quality data to be had in the EHR if you know where to find it. So I am going to go through a whirlwind tour of EHR data quality, which is a very interesting area of study with lots of great papers. Certainly don't have time to cover all of those today, but we are going to see a little bit of the theory behind this. Some of you may have read a very foundational paper in this space by Michael Kahn et al. From not that long ago, 2016, where he and his colleagues divide EHR data quality into these three categories. That we need to look for the following features in any EHR data set. We need to look for conformance, which says that the values that are in that data set meet the rules of the data model that the data is structured in. So if you're going with OMOP, do the variables in this table, are they structured in the way that OMOP spec says to do so? There's completeness, which is often sort of confused with, but for good reason, missingness, because we know that there is a lot of missing data in the EHR. Missing is sort of a funny concept when it comes to EHR data, in that data is not necessarily missing as so much as it is not present. If I don't go to the doctor, my data is not going to be in the EHR. I don't know if that means that it's missing necessarily, but we do need to take that into account when we're using the data. Then, of course, there's more traditional missingness, where if you have a bunch of deceased patients, but you only know the date of death for half of them, of course, that's something to contend with. And then there's plausibility, which is sometimes harder because it can be a little bit more subjective, but you do need to consider how believable the data values are, because not shockingly, human error causes, and technical error, by the way, causes strange data to come out once in a while. An example that I like to use is that once people are, of an adult age, their height should not drastically fluctuate over time. And if you're finding that it does, you may have plausibility issues. So let's go through some examples of where EHR data can go wrong and how it goes wrong. Data transformation is a huge part of all of our jobs as informaticians, data scientists, you name it. You always have to take raw data and transform it to something else. But just like when you save a photo over and over and over, and you end up with sort of these compression artifacts that you're seeing here in the example, with each data transformation, quality can degrade. And all of the examples that I'm going to go through here are things that can happen during transformation, some of which are preventable and some of which are less preventable. The first category I'm going to go over is mapping errors. So when you're mapping data from point A to point B, you can have simple human error. And in this example, you see that the raw data had ambulatory visits, and human error in that there was a human analyst that saw amb in the ambulatory and mapped that by accident to ambulance in the transform data. And then all of a sudden in your transform data, you have hundreds of thousands of ambulance visits when they should have been ambulatory visits. Obviously, this is something that would have a large impact on downstream analysis. And then there's another style of human error, which is more nuanced, I suppose, because it's content knowledge error. And I've actually seen this happen in a data set where you have two different creatinine labs that are quite different in meaning and context. And whoever's doing the data mapping just says creatinine, okay, I have a creatinine concept here in the transform data, and maps them both to the same lab. And then all of a sudden, any distinction between those two very different labs is completely lost in the transform data. Then there are granularity changes. And this is either a bug or a feature, depending on your perspective sometimes, in that if you are transforming data in order to make it sort of more, I suppose, easier to use for analysis, but less detailed so that it's easier to use for reporting, you often drop categories of long lists of things in order to make the categories more sensible. This, the example I have here is discharge disposition, where here at UNC, we have something like 40, maybe 60 different options for discharge disposition, very, very long list. And if you were transforming the data to use it for research, you might want to roll those up into higher level categories. However, that resulting aggregation that you get may not be granular enough for all use cases. So if I'm interested in looking at how many people were discharged to a skilled nursing facility, I'm not going to be able to do that with the transformed data. Now, this also means that when we aggregate things into these less granular categories, we need to be very sure that we are mapping those things correctly, because once they're rolled up, it's very difficult to unroll them. And if you only have access to the transform data and don't have access to the logic that was used to create that transform data, then you really you have to put a lot of trust in the person that did that mapping. Then there's loss of context. And this is where things can get really dangerous, because this ends up with data just not appearing in the transformed data that a user of the transformed data would never have any reason to know was missing in the first place. In the example on the left, you'll see that all diagnosis codes have a type. Some of them are patient-reported diagnoses, some are billing diagnoses, some are claims diagnoses. And if a well-meaning analyst wants to simplify the diagnosis data and drops that type variable, in the transform data, you end up with a list of undifferentiated diagnoses that you may not even know how to type at one point. And that may cause you to make massive misinterpretations of what those diagnoses mean. The example on the right is one that I saw in real life years back, where for financial data, for patient billing data, that was being used for research. All billing line items have a status, either final or void. And void charges, of course, are charges that were removed from the bill. But if that status field is removed, then all of a sudden everything becomes a positive line item, and you can actually completely miscalculate the total billing amount. So this loss of context can lead to some very scary errors in transformation. Now back to missing data, which I mentioned before is not always super straightforward to identify in EHRs. It is still an issue that we need to consider. And there are many reasons for missing data in the EHR, one of which I mentioned before, which is just, I don't go to the doctor this year, I have no data points. That sort of means there's data missing about me this year, even if there was data in other years about me. But there's also other causes. So one has to do with technical limitations. We here at UNC do a lot of genetic testing, but those genetic test results often come back, like you see on the right here, as this very detailed PDF with lots of nice pictures, sort of more of a dashboard display. But guess what? This is very much not able to be extracted, transformed, and loaded in the way that much of the structured data in the EHR is, despite the fact that you probably could mine a structured result out of this report. So if you were to look at the UNC genetic testing data, it might look to you as if we didn't do any genetic testing data because you wouldn't see any results in the structured lab data. That would be an incorrect assumption based on missing data. Another example is death data. So death data often comes from the state death index in whatever state your healthcare system is, in addition to your hospital. And so if you are getting a feed from the state death index, as many of our institutions are, including mine, that feed is not usually right up to date. I think we get ours quarterly, and even that quarterly load is about 3 months behind itself. And so you may look at the deaths from last month and realize that they look pretty unrealistic and that there aren't enough of them. But really what the issue is that there is a lag in death reporting that you need to consider. There's also individual variables that are sort of in the middle of the data that don't seem like they should be missing, that have a high rate of missingness. One example that has actually been really well highlighted in N3C is body mass index, or BMI. And you might think that's a pretty strange one to be missing because height and weight are such fundamental, vital variables. And while there are a lot of reasons that I won't go into for time's sake that BMI can be missing, one of my favorite reasons why it can be missing is, again, a very strange technical error where, well, I suppose error isn't even the right word. It's sort of, again, a feature where sometimes in the EHR interface, you enter a height and you enter a weight, and the BMI is calculated from the height and the weight, and it displays in the EHR. But just because it's calculated and displays in the EHR doesn't mean that calculated value is actually saved off into the database. And when that happens, to us, it looks like it was never there at all, even though it's sitting right in front of the physician's face. And so it always surprises people, understandably, who are very well exposed to BMI data, that it is often missing in the data. And then another totally different issue are really important variables like race and ethnicity, which can be missing for a wide variety of reasons, some of which start at the patient. Some patients aren't comfortable reporting race and ethnicity. Some patients don't feel like the race and ethnicity categories that we offer them describe them appropriately, and so choose to leave that blank. And so you will find sites that have half of their patients with missing race and or ethnicity data. And that is a fundamental issue of missingness that I hope that we can work as a community to correct over the next years. So in all of these cases, the transformation is not wrong. There's nothing technically wrong with these missing data transformations. But the data that come out the other end of the pipe are confusing and misleading to the user. And this kind of goes back to that PI that told me my data was junk, data were junk, in that it's true that from the way that he was seeing it, he saw a bunch of missingness, a bunch of holes, and there wasn't enough explanation to help him navigate that. And that was that's really the challenge that we had with N3C as well, knowing that there was going to be an enormous number of users trying to make sense of these data and not necessarily having a guide to walk them through it. And I'm going to explain a little bit about what N3C is for those of you who are not familiar with it, but you'll see kind of how we dealt with this, this sort of data Sherpa issue as we go forward here. Oh, finally, I do have one more example, which is sort of the easiest one, which is garbage in and garbage out. So I think we all know that if there is not well-curated data entered into the system, we're not going to be able to do anything with it on the other end. And there really are a couple ways to look at this. So on the left side, you see a case where we've actually, we meaning the data transformers, have messed things up. The data were entered correctly with a height of 6 centimeters. And when we transformed it, we mismapped the units, as I was giving an example of before, and we now have 60 inches. That is entirely the transformer's fault. However, the garbage in, garbage out problem is when the data reflect the source. And in this case, our clinician thought she was entering centimeters, it's a child's height, but the EHR was set to inches. And now we have the correct data, but clearly it's not a true fact about a patient. And in this case, there isn't a whole lot we can do on the data curation and engineering end. There are things that can be done during analysis to remove outliers and things like that, but that is certainly a tough case. Okay, so before I get into federated data networks and N3C's forebearers, I am going to give a little bit of background on what N3C is without going into too much detail. So the National COVID Cohort Collaborative is funded by NIH, specifically NCATS, and is led by Chris Shute, who you heard from, and Melissa Handel. And it is intended to be a network of data from institutions across the country, essentially any institution that wishes to contribute their EHR data about their COVID positive patients, along with some matched controls. And this data is held centrally at NIH in a very secure environment. And we harmonize the data so that it's all in the same data model. We use the OMOP data model, so that investigators, research assistants, and students, and anyone who can get an IRB to answer a COVID question and passes some approval gates can use a very large sample size to try and make really elegant insights about COVID. And I would encourage you to look up more information about N3C. I'm happy to put links to websites and such in the chat later. There's some really exciting publications coming out. There's a dashboard that you can look at to see kind of characterize patients inside of N3C. And it has truly been one of the most rewarding experiences of my career to work on, because it really shows the power of lots of different institutions coming together and being willing to share their data centrally. And that's a pretty big deal, considering the fact that prior to the pandemic, prior to when it was a public health emergency, there was limited institutional will, I think, at least in many cases, to share data with this level of sort of passion and freeness. And so it's really been wonderful to see. But in order to actually get N3C going, there was a lot of data engineering questions to answer. And a lot of that really had an impact on data quality. And that's mostly what we're going to talk about for the remainder of the time. But N3C was not the first group or consortium to try and do data harmonization in the same data model. There are wonderful federated data networks out there. A couple of them are Odyssey or OMOP, PCORNet, and I2B2 ACT and Trinetics are 4 of the different federated data models that have existed for years and have done wonderful work. But the difference between what they do and what N3C does is this word federation. And if you're not familiar with what federated data is versus centralized data, in a federated data network, instead of me sending a big payload of my data to a central location, I actually format the data in the chosen model, but I keep the data behind my firewall. And in those cases, when people want to analyze my data as part of a big network study, they actually send all of the different sites that are participating in the query, as opposed to actually having access to the data to query themselves. This can be a really nice model in that people do not have to share their data outside of their firewall. There are some limitations on what specific analyses you can do with that federated model, but it has certainly been a very successful model for those 4 networks that I mentioned, as well as others. Now, when I have my data behind my firewall, you may wonder how we can make sure that the data quality is good. Because if I am going to execute a query against 3 federated sites, that's a lot of trust that I'm putting in those sites to manage their data well. And so many of the data networks have great packages that they publish of code that enables you to do self-checks on your data. And going back to the framework, the CON framework that I mentioned earlier in the talk, these checks really check for elements in each of those categories. They're looking for conformance, they're looking for completeness, they're looking for plausibility, among other things. And you can see here on the slide that these are two examples of data quality packages released by these networks. The Odyssey data quality dashboard is formatted somewhat like a scorecard, as you can see, and enables you to see what specific areas, and in fact, it uses the CON framework in the way that it scores you. And you can see each of the areas where your site may be doing really well or doing really poorly, and use that in order to prioritize your fixes. And then on the bottom, you see the PCORNet data curation, which is very similar. Does give you some really nice visualizations in different data domains so that you can check to see where you might have data anomalies. And just as an example here, in April of 2020, this particular example site had a really large dip in visits. I would say, just off the top of my head, this probably has to do with the fact that lots of stuff was canceled in the beginning of the pandemic. But this visualization allows me to see that and make that diagnosis relatively easily. So, and there are other packages like this. IGB2 Act has one, Trinetics has one. These are what we wanted to build on as N3C when we considered our own data quality initiative. Because while we didn't want to reinvent the wheel here by any means, especially because these are such high quality packages, we knew that we had centralized data, which in many ways is an advantage when doing data quality because all of the data is co-located in one place. So we took this great foundational work and built upon it, changed it a bit so that we could do the best centralized data quality that we possibly could muster. So one of the reasons that it's really nice to have centralized data is that you can dig deeper into the data when you're trying to diagnose problems. If I am running a data quality query over a federated network, I might see that there's some funky looking data, but I can't necessarily interrogate why. So in this example here, let's say that I have a query that wants to count the number of inpatient visits that qualify for a particular inclusion criteria at a site, or for a study rather. In site 1, we have 45 qualifying inpatient visits, and site 2 has 27 qualifying inpatient visits, and then all of a sudden site 3 has 806. And I don't think site 3 is any bigger really than site 1 and 2, so clearly there's something going on. But in that federated environment, I'm not really able to go much deeper than this sort of aggregated count from an external perspective. Certainly I could go ask site 3 what's going on, and maybe we could have that conversation. But when the data is centralized, it does enable us to go into this row by row comparison on our own so that we can make quick diagnoses and quick fixes. If I were to have all 3 of these sites data in front of me, as you see on the bottom here, I can very easily see that site 3 has a bunch of duplicates or near duplicates that are causing their visiting count to inflate artificially. And if this were a site that I was working with as part of N3C, then we could go back and forth with that site, explain the duplicate issue, have them try and fix it if it's possible. And then in the next release of the N3C data, we would have a much smaller set of visits from that site. So let's get into the details of how centralized data quality works in N3C. I do want to point out that this is not just my work by any means. This is a huge team effort, and I am privileged to present the work on behalf of this large team. We do have a paper in JAMIA, the title of which is here, most of which I'm going to be covering in this talk, but certainly check that out if you'd like some more detailed information. And I also like to point out the fact that the sites that contribute to N3C, which now we have 67 released sites across the country, which is absolutely incredible. We would not have N3C without those sites and their data, so I would be remiss to not mention a big thank you to them as well. Okay, so I gave an overview of N3C, but I'm also going to give a little overview of our data ingestion pipeline, because while it's not completely related to the data quality stuff, I think it's necessary background information for you to understand how this whole thing works. So you see on the left side that sites are able to contribute to N3C in any of 4 data models. They can contribute in Odyssey or OMOP, ACT, Trinetics, or PCORNet. We're okay with any of them. And they do. We have examples from each one of those in almost equal measure coming in, and we do the transformation for them. We have field mappings and value set mappings that took literal thousands of person hours to create. That is tedious, intense work. And I like to point that out because I feel like people who do mappings are sort of unsung heroes of clinical informatics. And those mappings are what enable us to take raw data and move it to the OMOP model if it doesn't come in OMOP in the first place. So all that transformation happens. With luck, we don't introduce more transformation errors, as we were talking about at the beginning of this talk, and we end up with data that is all formatted in the OMOP data model. It's at this point where we execute a series of centralized data quality checks, and a new site that's submitting to N3C must pass those quality checks, at least our must-have quality checks, before they can enter what we call the harmonized release data set. And that data set is what investigators can actually use. So of course, we want the data that ends up there to be of very high quality. So here's where the pragmatism part comes in of between pragmatism and perfection. We cannot check N3C values against source systems. We can't re-identify the patients. That's part of our agreement. So there's not going to be any manual chart review that enables us to do that kind of really intense checking. We also are contending with 4 different sets of structural constraints from each of those 4 native data models that totally differ from each other, plus an extra transform to get those to the OMOP data model. So just like I was showing earlier, the example of saving a JPEG over and over again leads to compression artifacts. We have the potential for a lot of such compression artifacts because we transform so intensely. We also need to be really accepting of local idiosyncrasies. And when I created this slide, we had 66 sites, now we have 67. And I think the example I showed about sort of wonky looking visit data is a really good example of a local idiosyncrasy. It could be that that site for EHR structural reasons or for billing reasons needs to have all of those duplicate visits in their data. That might just be part of their native data spec, and we need to accept that. In those cases, it's imperative that we at N3C figure out ways around that, way to deal with that without imposing on the site to change for our sake. And then it's sort of connected to that, N3C's priorities may or may not match the site's priorities. So if we see a bunch of implausible data for a particular lab that's important to us, we can tell the site about that, and we do, but the site may put that somewhere in the middle of their to fix list because they may have more important fixes that are essential for their local operations. And so all of these things really make it so that we need to expect the best we can of our sites without being too draconian and not letting perfection get in the way of the absolutely good enough. And so certainly we take the pragmatic approach. This is a really good example of that pragmatic approach, specifically having to do with the fact that we have 4 different starting data specs to work with here. Death data is supported in all 4 of the different models, but as you can see, it's not supported in exactly the same way. So in OMOP or Odyssey, you can see that death data is supported, that death date is required in order to call someone deceased, that death cause is supported, so you can enter a cause of death there, and that it also has a spot for discharge disposition, so that you can see if somebody was discharged from the hospital as expired or deceased, even if they don't have death data recorded elsewhere. If we move down to the other models, though, you'll see that things start to change a bit. In PCORNet, death date is not required to call a patient deceased, which makes it very difficult to conform to the OMOP model, because once we move PCORNet data into OMOP, all of a sudden we're breaking the rules of OMOP if we don't have a death date. Moreover, in Trinetics and ACT, those 2 models do not support entering death cause or entering discharge disposition, which can make the data look missing from Trinetics or ACT sites, when in reality, it's not, well, I suppose it is missing, but it's not the fault of the sites that it's missing because the models that they use literally don't support it. So rather than just sort of throwing up our hands and saying, well, I guess we can't have death data, what we do instead is choose to break rules where it makes sense So we do allow null death dates in OMOP, even though OMOP doesn't allow null death dates, because we have to in order to make this the most harmonized and yet usable data we can, hence the pragmatism. So we run a set of minimum checks against the data that we receive in N3C in order to make sure that it is good to go for use in research. And I promise you I will not read through all of this text, but I am going to give you some highlights of the checks that we run. The first one is pretty simple in that we make sure that the input data is following the rules of the input data model. So if you tell me you are submitting data in PCORNet format, but your data does not look like PCORNet, then we're not going to be able to accept that. So that's pretty straightforward. Demographics are sort of subjective in a way in that we make sure that the number of patients that you're submitting, as well as the distribution of their demographics for the site that you are coming from, look reasonable. And reasonable is where that subjectivity comes in. Now, if UNC only submitted a set of 500 patients to N3C, that would not be reasonable because we have had many, many more COVID cases than 500. So it's really at the ends of the spectrums that we can sort of declare that things are not reasonable. If something is maybe 100 patients off, we're probably not going to catch that, but we do look for those extremes. For COVID tests, and just remember that because N3C is a COVID research data set, COVID data and especially COVID tests are incredibly important to us, so we focus a lot on those. And we require that all COVID tests are coded with a standard concept according to the rules of your input data model, and that all test results are also standardized. Now, we do not enforce this check for other labs. And the reason for that is that it is incredibly labor intensive for EHR data engineers to map every single possible lab result for any possible lab to a standard vocabulary. In a perfect world, that would be the case. We would have all of the labs and all of their results standardized, but we knew that that wasn't a reasonable ask. There's pragmatism again. For COVID tests though, because again, they're so important, we said, you know what, forget the rest of your labs. For COVID though, we know that you're going to have some labs that are positive, detected, not detected. I saw one at my site that literally said unpositive as a result, despite that not being a word. And we want all of those mapped to a standard concept so that we can be sure that our researchers can identify who had a positive COVID test. For conditions, similarly, we really laser focus on COVID data. So we look to make sure that there are a reasonable number of clinical encounters in patients that are attached to a UO7.1 diagnosis, which is the ICD-10 code for COVID. And there are many sites that initially submit data with no UO7.1 diagnoses because it's a new ICD-10 code. Sometimes it gets missed in the data transformation. And so that's an instant check for us that we know that you're missing some stuff if you have no patients with a COVID code. For encounters, encounters are sort of a pet data domain for me. I think that they are extremely important and extremely messy, which makes it a fun project. And we try to make it as less messy as possible, even though we know that there's going to be a lot of differentiation between sites per our examples before, where I want to make sure that every site has a reasonable distribution of different kinds of visit types. So I don't want to see only inpatient visits. I don't want to see only emergency visits. I want to see a mix. And I also want to see that the majority of inpatient visits have end dates because we want to assume that patients do get discharged from the hospital and that you don't have lengths of stay of 10,000 days. All of those things sound very sort of ludicrous in their severity, but we actually have seen things like that. And that is a result of the visit domain just being very, very complex. Now, for measurements, measurements and observations, that's sort of an OMOP way of coding things that are either labs or vitals or other stuff like smoking status that you can attach to a patient. Here, we're looking to make sure that a site supports a good number of unique different kinds of observations. If you send me an observation table and you're only measuring one thing, then we're just going to question if your data is rich enough to be used for research purposes. So that's what that check is. And then there's some additional checks, which I won't go into detail with here, but they're very technical checks, but are very important ones. Things like the primary keys in your table are all unique. The people in your data are all in your person table, things like that. And there are some sites that get stuck there, but those are almost always fixable issues. And then finally, there's this sort of squishy category, but it's actually one of the more interesting ones for me, which is fitness for use. And this is because the N3C data is used for such a wide variety of purposes that there's no way on earth that a centralized data quality checking team, like the one that we have for N3C, could think of every possible check that needs to be run and execute on those. Rather, we have researchers that are using the data for a particular purpose and give us a heads up when they see things like, hey, I can't find any BMI measurements at this particular site. Those are things that we can then go and investigate and make sure that the data, as much as possible, can be well suited for that researcher's particular purpose. So that's been really interesting to see what kinds of things are really important for downstream users. And that has really improved the data quality in many ways, just from those flags that they send up. Through all of this effort, we have come up with a list of data quality heuristics that we think have really characterized most of the different data quality issues that we see in site data. The number one thing that we see are, and actually I would say this probably surprised me that this was the number one issue, but the number one issue was that people weren't complying with the rules of the data model that they were using to submit. So if PCORNet, and I'm making this up, suggests that male gender be classified as a 0-1 and female gender be classified as a 0-3, etc. I'm making that up. And you're submitting data with M and F instead, then you're not complying with the rules of PCORNet and we are unable to process your data correctly. You see a lot of errors like that. The other ones are more things that you might expect. So the COVID test, because we are a little more stringent about that, we do see a lot of non-standardized COVID tests coming in. We do see a lot of implausible visit types. So I was mentioning if a site sends 100% inpatient visits, we know that's not correct. And as I mentioned, and I'm sort of skipping around here, but we do see a lot of lack of U07.1 codes, and non-unique primary keys, and lots of other things that I would suggest that you read through in the paper if that's something that you're interested in. But the point is that these heuristics allow us to really focus our checks on these areas because we know that these are the places where most sites tend to have issues. And when we go back to sites with these issues, generally they're pretty grateful to hear about these things because they may be things that they never even noticed in their data until we let them know. So as an example of some of these heuristics, I want to just go through a couple of visualizations that show how the work that N3C has done has actually changed data quality both inside of N3C and at the local sites. So heuristic 2, which is that the COVID test results are not standard. What you're looking at here is a subset of our sites, and each colored line is a site. And at the beginning, so on the left side, that is the percent of their COVID test results that were invalid. So you can see that this orange site, 100% of their COVID tests were not standardized or null. This site, probably about, I don't know, 68% or so. And these were all sites that we communicated with to say, hey, your COVID tests are not where we expect them to be. And what I really like about this visualization is that it shows that after we had that conversation with them, their percentage of invalid test results really plummeted, in most cases to 0, in some cases just above 0. And you can see here in the shaded area, this is the mean of percent invalid COVID-19 test results across all sites. So you'll see that most of them got at least around the mean, which made us very happy and was certainly a huge improvement over where they started. Moreover, that implausible visit type distribution I mentioned, what you're seeing here is 2 different examples of implausible inpatient visit percentage. So this particular site had a 12% inpatient visit. So that means that of all of their visits, 12% of those were flagged as inpatient. And we have found, based on what we see from other sites, that that's quite high. You can see where the mean percentage is here, which is quite a bit lower than 12. And while this could be true, there could absolutely be a site that does 12% inpatient visits. We had a feeling that it wasn't based on where the site was, who the site was. And lo and behold, it was a mapping error where they were mapping outpatient surgeries to inpatient visits, which was not the case. And once they made that change, again, they plummeted back down to where we think they probably should be. And again, I want to point out that this change didn't just occur in N3C, but now the site's local data is also of better quality too, which is exactly what we want. We want this to be beneficial to sites and not just to N3C. The opposite problem occurs when sites send us data that has almost no inpatient visits or very, very few inpatient visits. And you can see that after discussion with these different sites that all have that problem, all of them raised, in some cases somewhat, and in some cases quite a bit in order to get closer to the mean. So I've talked a lot about communicating with sites and telling them about their data quality issues. And we consider this a really virtuous cycle of improvement where we get data from sites, we do the quality review, we send really detailed and friendly feedback to sites. And then most of the time, sites are very, very happy to make those corrections because they see benefit in it for themselves as well. They send us new data. And then sometimes there are more issues to correct, and we keep going through that cycle until all of our minimum checks are passed. So I'm going to close out by talking about some of the things that I think are particularly beneficial about having centralized data quality checks versus being only able to use federated data quality checks, and some of the directions that I think we could go forward with centralized EHR data, even far beyond the N3C and the COVID use case. So I think probably the most compelling argument for centralized data quality checking is this ability to benchmark from site to site. And you saw this a little bit in the example I gave with the different visit counts per site that you could then interrogate the detail of when you could get access to the row level data. Similarly, you can do those kinds of comparison checks in any other data domain, not just visits. And in this case, this is a real heat map that we produced for sites to show them where they were lacking in coverage of certain kinds of labs when compared to their peers. So if you look up a column, you'll see, and this is a fictitious site ID, but you can see that this site has pretty good coverage of all of these different vital signs that you're seeing here, but pretty poor coverage when it comes to these two vitals up here. But one thing that you can also see is that most of their peers have similarly poor coverage of these two vitals, except for these guys over here. And for me as a site, if I saw that, I would want to prioritize making sure that I at least had good coverage of some of the vitals that my peers had good coverage of. And even if I did want to improve the things that many people were lacking in, I would know that maybe it would sort of socially acceptable for me to be missing that if so many of my peers were as well. I actually think this guy is a particularly good example in that you'll see that most of their peers, the majority of their peers, have really good heart rate coverage, and they appear to have good coverage of many vitals, but very poor coverage of heart rate. If I were site 50 in this fictitious example, I would definitely focus on heart rate and try to see how I could harmonize that as best as possible. This kind of benchmarking is incredibly powerful and is something that centralized data really makes possible. Moreover, kind of going back to the fitness for use bit, I think that the ability to crowdsource data quality is really exciting in that, as I mentioned, no team of people is going to know every single thing that they should look for at every single site, but our researchers do. And all of these examples are things that we really did hear from various researchers about data that they saw from different sites. So in one case, they saw a site that had their pulse measurements labeled with millimeters of mercury, not the right unit. And so we were able to get back to that site, and lo and behold, that was an error on their part that was fixed. Sites that were totally missing any COVID deaths that made it look like no one had died of COVID at that site, when that was certainly not the case. That was a missing data issue that we were able to work out. And then a coding error where it looked like no one, I don't know if it was actually diabetes, but it looked like no one had a particular common disease at a site. And again, that was a mapping error that we were able to adjust with them. These were all things that came directly from researchers because we have centralized data. And then there's the economy of scale piece, which is also a really nice benefit of having data centralization. Having more data available in the same place allows us to do work like unit harmonization. So this is not work that I did myself, but was led by Richard Moffat and Kate Bradwell. And this was work to look at labs holistically over the entirety of the M3C and try and rescue lab data that had either no units or the wrong units by looking at other labs, the same lab at other sites to see if you could maybe infer those units. Really ended up rescuing a ton of data that might not otherwise have been usable. And that is really only possible when you have a ton of data in the same place to examine in that way. And then because we have a centralized data quality team, you have more eyes on your data, which is almost always a good thing. And you get new perspectives on your data. Just like when you're writing a paper and you've read it 35 times and you can't see any of the typos anymore because you're just too close to it. Sometimes having other people able to look at your data from an entirely neutral perspective really reveals things that you may not have noticed. And I think we've really seen that. I mean, it's anecdotal evidence, of course, but we've seen that with sites sort of saying, oh man, I never noticed thing X that you're pointing out to me. And it's very gratifying to be able to help sites out in that way. So the takeaways from all of this is that the data quality analysts that I am privileged to work with as part of M3C have such deep subject matter expertise, and we have access to very powerful analytical and visualization tools. And all of that together can be used to benefit sites directly and make rapid data quality improvements in high priority areas for M3C and high priority areas for sites. Those centralized data quality checks are not intended at all to replace federated data quality checks, which do happen before sites send their data to us. So a layer of data quality checks have already happened locally, local data quality checks, federated network checks. And then by the time we get the data at M3C, we are performing a third layer of checks that is intended to augment those previous layers and build on them. And we like to think that that's a sum greater than its parts. As I just mentioned, centralized data quality enables us to do benchmarking and crowdsourcing and take advantage of scale-based efficiencies. And all of this comes together so that we can say, I think with a lot of confidence, that an ideal model for data quality assessment is a combination of those local checks by personnel who intimately understand their site's data, those federated checks if the site is part of a federated network that really do a nice job sort of characterizing the big issues that a site may need to take care of before submitting to something like M3C, and then centralized checking on top of all of that to sort of catch the straggling errors and clean up the rest. And with that, that is what I have to come talk to you about today, and I would be very happy to take any questions that you might have.
Thank you very much, Emily. That was extraordinary, and though I expected no less. There are several questions appearing in the question and answer area. I'll read one of them. How do you measure the information loss during the mapping process? Any suggestions to remedy the loss?
I have to think about that because that's an excellent question. The way that I have done this in the past, and I'm not suggesting that this is the best way or the right way to do it, but visualizing the areas where you have done vocabulary mappings specifically can be very helpful in determining where big errors have occurred. The hard ones to find are the tiny errors, but going back to the ambulatory ambulance example, if I know that I have manually mapped my visit type vocabulary from source A to source B, and I visualize the distribution of how many visits are in each one of those categories. In source A, I'll be able to see, probably like most healthcare systems, that the majority of my visits are ambulatory. And then if I look at the same distribution in source B, I will see the same curve because it's exactly the same data, presumably, but I will see that ambulance is now taking up most of the space. That is a very manual way of checking, which is why I don't know that it's the best way of doing it. But I do think that vocabulary mappings specifically are the most dangerous of the mappings in many ways. And so doing those kinds of manual checks are well worthwhile, I think.
I'll read the next one verbatim. What can clinicians do to improve the quality of data collected? You mentioned feedback to organizations on the quality of their data. Could there be feedback directly to clinicians and centralized data quality checks? Would this be beneficial to either?
So that's another really excellent question. I have always been very sensitive to that in the past, perhaps oversensitive, because I understand from my clinician colleagues how much they are already expected to do in the EHR to the point of having to stay up all night to chart. And I have immense empathy for how they are expected to interact with the EHR on a daily basis. So I have tried in some cases to sort of suggest, you know, if you collected thing A in a more structured format or entered it this way, it would be easier for data analysis, but I never really expected those changes to come to pass. But I'll give you a more hopeful example based on a conversation I literally had yesterday morning. I was speaking with the director of the long COVID clinic here at UNC and just kind of getting his thoughts on the data that's being collected about long COVID patients, because, and we didn't talk about long COVID in this talk, but long COVID is incredibly hard to identify using structured data. They just introduced a diagnosis code for it in the start of October. There's not a good clinical definition right now, so it's very squishy. And when I was speaking to him about this issue, I said, how are you coding long COVID patients? And what he told me was that most of the signs and symptoms of long COVID are things that end up in his clinic note, as opposed to in a structured format. And I talked to him about the fact that while we can do some great things with NLP, what we're seeing is a real lack of things like fatigue and brain fog and confusion in the structured data. And he actually said to me, well, now that you've told me that, then that will make me actually want to start entering those diagnosis codes more frequently in a structured way so that, you know, people like you doing data science can take advantage of that more. And that made me sort of consider the fact that I think that just telling clinicians you should enter data better in general is probably not going to get us anywhere, but really use case-based behavior changes, like my conversation yesterday, where this particular physician has an immense interest in making long COVID research better, and I have an immense interest in doing long COVID research. It's mutually beneficial, and he was willing to make that behavior change. And I think that's probably how we're going to get it done.
So the buzzword of the week that you haven't mentioned, Dr. Pfaff, is fire, HL7 fire. And what are your speculations that the Office of the National Coordinator, as they increase the rigor and completeness of the US Core implementation guide for fire, which EHR vendors have to conform to under penalty of who knows what, will that contribute palpably to improved data quality, in your opinion?
I think yes and no. I think there are many improvements to be made by having a national and enforced data model. And while FHIR fits much nicer as a data exchange specification rather than a common data model in and of itself, I think that it does have some of the features of the data models that we've talked about, PCORNet, OMOP, Trinetics, ITP2, et cetera, where there is an expected structure and there is an expected vocabulary for each of the terms, which probably goes a long way towards taking some of the local variation out of data and makes it easier for further harmonization down the line if you're not starting from a completely local code set that has absolutely no bearing on any standards. I don't, however, think it is going to change a lot of the issues that we're seeing when it just comes to those local idiosyncrasies in data that we just need to understand and work around when we're harmonizing data. I hate to use the visit example again, but I do think that that's a perfect one for FHIR, where if you are an institution that insists on making a new inpatient visit every single day of a patient's stay, as many sites do for billing reasons, FHIR isn't going to help that. They're going to represent the data in the way that you feed it in. And as long as it follows the rules of the spec, you can still have funky looking visit data. If we try to harmonize that, we're still going to have to work around that in order to truly harmonize the data so that we can use it. So yes, I think it will help. No, I do not think it will be a 100% magical solution, although I suspect that some people are hoping that it will be.
Yes. And I think we have time for one last question, which I will read. Is there a way IT technology departments, that is software, hardware handlers, could have helped make startup, I presume N3C startup, any easier? Anything more that can be done to help now?
Sometimes data transformation, data engineering, rather, I'll just make it a bigger category. And by that, I include people who are ETL developers, data engineers, hardware folks that support databases. Sometimes I think that, especially in the research space, it is expected that folks can do all of the work to build a new data model, let's say a local OMOP instantiation, on a shoestring with like 2 people. And I've seen that time and time again, including at my own site. It's generally underfunded and underappreciated. I could whine about that for a while, but I do think that there should be recognition that that is often the case, and that if institutions invested more in those operations, were sort of willing to put up more funds that might not be super sustainable, they might not get back, but do this upfront investment in making a really excellent OMOP model, making a really excellent PCORNet model at their institution, then I do think that that upfront investment in those, in good hardware, in excellent data engineers, in wonderful terminologists who can help with mapping, will make a resource at universities that will pay off tenfold in research opportunities, in collaboration opportunities, and grant opportunities in the future. So that is one way that I think we could all really do better in this space, is just by investing more on the front end of these activities.
Dr. Pfaff, thank you very much for an enlightening and insightful talk. I'm quite sure you'll be willing to address questions that might come in at a later time. We can send them to you. But in the meantime, we appreciate your spending your time with us. And to our audience, thank you for joining us today at the Biomedical Informatics and Data Science Grand Rounds. We always strive to bring some of the best and brightest people in the country. And in my opinion, Dr. Pfaff is certainly in that category. So thank you again.
Thank you so much. Very happy to be here.